In practice, there are affinities between system architecture and programming models. Identifying such affinities is important because in practice you might find yourself in situations where either the programming model or the system architecture are given and cannot be easily changed. The system architecture is fixed when there is an existing infrastructure to work with, how machines are organized in a data center, a network topology, or a geographic distribution of resources. The programming model is often fixed when the distributed system needs to be developed in the scope of an existing ecosystem in which it needs to integrate into, or if a development team or even an entire organization has a preference for specific programming models. Let's look into an example together. This structure is called a systolic array. In this programming model, every processing element, here the PIJs, in the picture, compute part of the results individually and in parallel. The processing elements are arranged in a matrix and they calculate their new state based on the inputs of the neighboring nodes. After every turn, the new outputs are sent on to connected neighbors. Now, with such a programming model, there is plenty of communication, and you would want to use it with a network that has a high degree of interconnectedness between the neighboring nodes. If your network topology was linear, with a single bus in the middle, this model would not scale well. The next one is pretty famous. You all know functions or procedure calls in regular programming languages, right? Remote procedure calls, RPC, turn that into a programming model for distributed systems. The client calls a function, but instead of local execution, the function is invoked on a remote machine. Here we have a function that registers a player with a game server to start a new session. The trick is that the client function call operates against a stub, which creates a message instead of calling the actual function. The message contains the function name as well as the argument values. This message is then sent through the network to the server machine which hosts the remote function. Here, the server-side stub locates the requested function, recreates the argument values, and performs the function call on behalf of the client. Indeed, the return value is then sent back to the client through a message. So from the perspective of the client, the fact that the function invocation happened on another machine is transparent. Now, this programming model is clearly point-to-point, which means that you can use it very well with a number of user devices which all call a central server or a farm of servers if you need to scale it larger. But it does not work very well when the user devices need to communicate with each other, because this is more of a group communication problem than a point-to-point problem. So you see, choosing the right combination of programming model and system architecture matters.